So part 2 to wrap this up. So in this particular one, here, let me hide myself a little bit because I'm kind of in the way. I've got to get my cursor back. Hang on just a second. Okay, there we go. All right. So a quantity of 50 milliliters of water is added to 80 degrees. At 80 degrees Celsius is added to 50 milliliters of water at 20 degrees Celsius. What would be the final temperature of the total volume? Hang on, what's different about this? Oh, look here. I have no source of heat. Instead, I have warmer water. I have water at 80 degrees, and I have water at 20 degrees. So where is the heat coming from? Yeah, the heat's coming from the warmer water. So there's going to be a transfer of energy here. What do we know about energy and its transfer? Because we know a law. Yeah, the law of conservation of energy says that energy can't be created or destroyed. So we know that the energy that is in the 80-degree water is going to transfer to the 20-degree water. So that must mean that the Q of the hot water, oops, sorry, I don't know what happened there. The Q of the hot water went go into the Q of the cold water. Well, we want to set these equal to each other somehow. So what's happening here? The Q of the hot water is being lost, and the Q of the cold water is being gained. Okay. So, losing means it's minusing. So I think maybe we can set these equal to each other if we said that it was minus there. So maybe if we said minus Q lost, and that would be equal to Q gained, because you can't have, like, if you have 20 joules that are lost, that's not equal to 20 joules, is it? But if I set it negative, if I make it negative, then these become equal to one another. All right, so let's start over again. Let me get rid of all the ink there. All right, so let's see if we can figure this out. So we have 80 degrees for the temperature initial for this one, and 20 degrees for the temperature initial in this one. The temperature final should be the same. They should end up at the same temperature, so the temperature final should be X for both of them. The mass here, we have 50 milliliters of each kind of water. So hang on, we know something because we just came up with this proportionality that Q was proportional to mass times the change in temperature. And we just said that Q lost was equal to the Q gained. Okay, this is L and this is G. All right. So what if we did that? What if we said, okay, negative 50 grams times X minus 80 is equal to 50 grams times X minus 20. Okay, so let's go ahead and distribute through. So we get negative 50X plus 4,000 is equal to 50X minus, let's see, 5 and 2, that's 1,000? Okay, 1,000. Okay, so to solve this, let's see, I'm going to add 50x to both sides, right? And then I'm going to add 1,000 to both sides, because remember, I want to get stuff on the same side. So here we go. So I've got 5,000 is equal to 100x, which means, oh yeah, that's 50 degrees Celsius. Okay, 50 degrees Celsius. So the final temperature is 50 degrees. Now, we could have looked at this in a different way instead of mathematically. If we looked at it and said, okay, well, that's 60 degrees between the two, right? 60 degrees between the two. Half of that is 30. So 80 minus 30 is equal to 50. And 20 plus 30 is equal to 50. We could have figured it out like that, but this is the mathematical way of doing it. So two ways of going through that problem that really get us to where we need to go. So question 5 says a quantity of 50 milliliters of water at 80 degrees is added to 100 milliliters of water at 20 degrees. What would be the final temperature of the total volume? So here we go again. We have the temperature initial at 80 degrees and 20 degrees. The temperature final, remember, should be the same for both of them. We know the mass is 50 for this one and 100 for this one. So let's do that again. So we had negative 50 grams, right? Minus 50, yep, times x minus 80. And that's going to equal 100 times x minus 20. Okay, so this was the same as last time, so we have negative 50x plus 4,000 is equal to 100x minus 2,000. All right, so add 50 to both sides. Add 2,000 to both sides. I'm doing it at the same time. You guys are probably used to doing it separately, but I'm doing it at the same time. So we get, that goes out, and we're left with, 2,000. We're left with 6,000 is equal to 150x. So 6,000 is equal to 150x. So let's see. Using my calculator really quickly. And I get that x is equal to 40 degrees. 40 degrees. So, yep. And that makes sense. Why isn't it straight in the middle? Well, let's see. I have 100 milliliters of 20-degree water. So the water is going to be closer to the 20-degree mark than the 80-degree mark because I have twice as much water here. So that makes sense. Okay? So let's see if we can find the final problem. A quantity of, so in the last two problems, what we've seen is that the energy released and the energy gained are in concert with one another. And so we can use that fact to figure out how much energy is gained by one or how much energy is lost by the other. And all we have to remember is that negative sign. So things that are hot are losing heat are going to have a negative sign in front of it, and things that are gaining heat are just going to be positive because that's where the heat is coming from. Heat always goes from hot to cold. Always. It always goes from hot to cold. If you think about it, you say it gets cold, but what's actually happening is the heat is rushing out into the cold air because it's always going from hot to cold, leaving behind an absence of heat or cold. There you go. All right. So a quantity of 50 grams of water at 80 degrees Celsius is added to 50 grams of ethyl alcohol at 20 degrees Celsius. What would be the final temperature of the total volume? Hang on, something here is weird. I see water and I see ethyl alcohol. Those aren't the same. So let me think a little bit here. I know something about alcohols. Like, I'm not sure about ethyl alcohol, but I know something about alcohol in general. If I put water on a hand and alcohol on a hand, the alcohol evaporates faster and gets cooler faster than the water does. I wonder if that is going to change this whole idea. So I can't really compare this without knowing more information. And the piece of information that we need to know is that in order to make this equation that we've been trying to develop an equation and not a proportionality, we have to have a constant that has to be added here. And since we were always using water, the constant didn't matter because it fell out because water was being used. But because we're using ethyl alcohol, it makes a huge difference. Okay, for water, there's something called the specific heat capacity. The specific heat capacity for water is 4,184 Okay, for water it's 4.184 joules per gram degree Celsius. Now that's pretty interesting because joule is the heat unit. There's our mass unit. There's our other unit. So this is for water. Okay. And then the C4, so that's for water. The C for the alcohol is 2.3 joules per gram degree Celsius. That's for the alcohol. Okay. So what we have to do here is we still know because the water is warmer, so negative Q of the water has to equal the Q gained by the alcohol. Okay, we still know that. But it seems like we're going to have to add this extra component in there because otherwise we can't compare these two things. So what do we know? We want to know the final temperature. So let's start writing some things down. I'm going to erase this. Hopefully you have this down. Okay, so temperature initial. I'm going to put water and I'm going to put alcohol over here. So the water is 80. The alcohol is 20. The temperature final is the same for both because we're mixing them together. The mass, we have 50 grams of water and we have 50 grams of ethyl alcohol. And now we know that there's this constant, and for water it's 4.184 joules per gram degree Celsius, and this one is 2.3 joules per gram degree Celsius. Okay, so, and we also know that the Q of the water is equal to the Q of the alcohol. So the negative Q of the water, the amount lost by the water, is equal to the amount gained by the alcohol. So negative 50 grams times 4.184 joules per gram degree Celsius times x minus 80 equals, 50 times 2.3 joules per gram degree Celsius. There should be grams right there, sorry. Times x minus 20, and that's in degrees Celsius. So we see that grams are going to cancel out, degrees Celsius are going to cancel out. Okay, all of that's going to cancel out, leaving us with only joules. So now it just becomes a calculation. So we get negative 1.819 times x minus 80, and that's going to equal, let's see here. Oh, hang on, that's not right. I did something wrong. 1 second. Okay, that's not right. I did something wrong, so let me calculate. So I get 50 times 4.184, and I get 2, sorry, I'm still on eraser, 209.2 joules times x minus 80 is equal to 115 joules times x minus 20. So I get negative 209.2x plus 16,736, which is equal to 115x minus 2,300. Okay, so I'm going to add 209.2 to both sides, 209.2x to both sides. I'm going to add 2,300 to both sides. Okay, that cancels out, that drops out, and I get 324.2x is equal to 19,036, sorry. Can't write very well here. And I'm going to divide that by 324.2, and I get X. I'm going to come up here. Okay, X is equal to 58.7 degrees Celsius. That's what I'm going to end up with. So we've just learned, that we had to add this constant component here. So what do we know now? So we have this right now, but we know that there's something missing here, and we know it's because Q is proportional to this constant as well. So the constant has to go into the equation. And now we get this equation that Q is equal to M times C times delta T. And this equation is called the specific heat equation. And it's going to be very important to us. Okay? So hopefully that's giving you enough to chew on. Tomorrow we're going to be practicing specific heat problems. So make sure you've taken both of these sets of notes. Sorry, this one is a little bit longer. Thank you.